Okay, here we are at day 6. Sorry for a late start. I'll compensate for it by ending early. Um, well, actually, that's not entirely true. What happens regarding getting to class really depends more on you guys, because my plan for today is I have some new things to cover that are meant to set up the second assignment, which I'll put out on Tuesday. And then uh, after that, I want to throw it open to any questions about the first assignment, and we'll just see what kind of questions you guys have. And also like to take some time, if unless you're already finished with it,
Done.
to in case you're struggling with anything, and don't have to ask questions like right out in the open to be immortalized on YouTube. So we'll just see how that goes. Okay, so yeah, the assignment's posted here on the assignments page. Makes sense. And as we go on the lectures page, is where I'll put where I'm putting everything else, but like due dates are here as well. So the second assignment I'll also make due following Tuesday, July 3rd. So yes, it's the day before a holiday, but I'm still going to be here, and you should be too. And but after that, I'm traveling. But start thinking about what you'd like to do for a more substantial project during July, for something like maybe relates to your research. I'm already starting to get input on that if people want to do their own thing, which actually I prefer. So just to plant that idea in your head. Okay, now the theme for today is numerical linear algebra. To have you guys up and running with essential tasks for that. And that means we're going to be, for the first time, getting into SciPy. We've been using NumPy already, but so NumPy and SciPy work together. You use functions from NumPy to, for example, create matrices, but then to actually work with them, perform linear algebra tasks, SciPy is needed. Also, SciPy is needed for sparse matrices. So you may recall that MATLAB has different structures for dense and sparse matrices. So for dense matrices, it's a conventional two-dimensional array. Whereas for sparse matrices, the data structure that keeps track of all of the non-zero entries. And Python works like that as well, except that in MATLAB, you really only have one built-in way of representing sparse matrices, whereas in Python, very many different kinds that have their advantages and disadvantages for different situations. Okay, so what I'll do is I will start by playing around with some functions that are provided by SciPy, and then we'll take a look at I'll be running some code to implement these things. So I'll show you what wheel they provide, and then how I would reinvent it. And that'll set the stage for the second assignment. So just like in the first assignment, I implemented forward Euler for you, and then you are building on that by implementing higher order methods in a similar way. Same thing here. I'm going to show you how you would handle Gaussian elimination without pivoting, and then you would build on that to add pivoting, forward and back substitution, and also we'll look at some iterative methods. Okay. Now, so I have some things to import. Actually, a lot of things that I will need today. So I will need standard math functions. we'll still need NumPy as usual. And now some things from SciPy. For what I'm doing today, I don't need to import the root of SciPy itself. It's all sub-packages that I need. So SciPy has a linalg package. I'll abbreviate it as SCL. Now keep in mind, NumPy has a linear algebra package, linalg package also. For instance, it has the norm function that you'll need for your assignments. But it's a linalg package that, for instance, provides for solving A equals B, so a Python equivalent of backslash. I also want to work with sparse matrices. So there's a sparse subpackage for that. And finally, under sparse, there's a separate subpackage for linear algebra operations on sparse matrices. So I'll abbreviate that as SPL. Okay. But what we'll see is that the linalg package for sparse matrices is very limited compared to the one up here for full dense matrices, just because certain eigenvalues, certain algorithms, such as computing eigenvalues, they don't go so well for us. They don't translate well to sparse matrices because the algorithms involved tend to destroy sparsity. Okay. Now, let's see. So what I'll do is, okay, I'll just jump into working with sparse matrices. So using my sparse subpackage, I'm going to create a random matrix. Now, to make it easier to see in a screen, I'll keep it pretty small. Let's see if I get away with like a 4x4. Now, there's different arguments you can choose when it's random. Density indicates the percentage of non-zero entries to have, by default being 1%. Now, I'm actually going to make this not very sparse. Just so we something to demonstrate. Because also, if I'm going to be solving systems, I want some assurance that the matrix involved will be non-singular. Now, format, very important. The default format that's shown here on the screen is COO. That's short for coordinate. That is equivalent to MATLAB's representation of sparse matrices. So coordinate format is you have a vector of row indices, a vector of corresponding column indices, and then a vector containing the entries. So you can say, at this I, at this j, is this entry aij. So if you have n non-zero entries, your storage is 3n. Numbers altogether, although 2n of those are integers. That's less storage. Now, one of the things that's with using sparse matrices in Python, it's a double-edged sword. Because on one hand, it's nice to have all these different formats available, unlike MATLAB's just for one. Because some formats really are better than coordinate format for certain tasks. They're more efficient. But then, you have to be able to use the right format for the right task. Some things you just can't do. For example, in coordinate format, you cannot access aij using conventional notation. It won't allow it. So I'll show you, in fact. Okay, so I'll just go ahead and accept the default format. Now, here's another thing that's annoying about sparse matrices in Python. I want to see what A is. It tells me there are 9 stored elements. That means there are 9 non-zero entries out of a possible 16, which makes sense because 16 times 0.6 is 9.6. So I got that right. And I can see the number of non-zero entries. a dot nnz, which is equivalent to MATLAB's nnz of a, and tells me here's how many non-zero entries there are. I can also do a dot shape, which is similar to size a. We've seen this already for full matrices. That part works the same. Okay, but let's suppose I want to look at an entry, like the 1, 2 entry, which is 0, 1. So row 1, column 2, because it's zero-based indexing. And it's not going to like that. Can't do it. It says it's not subscriptable. So MATLAB does let you do this with coordinate format, but not Python. Pretty annoying. Okay. So at this point, I don't even know what's in this matrix. There are 9 non-zero entries in this 4x4 matrix. That's all I know about it. Fortunately, there is a way, although you wouldn't want to do this with large matrices, but use a two-array function, which is equivalent to MATLAB's full of A. So that converts a sparse matrix A to a full matrix. And there you can see all the entries. Okay. All right. Now, but now what I want to do is I want to be able to actually look at entries. So I'm going to go back and recreate this matrix and actually specify a different format. So the format I'm going to use here is CSR, for that's short for compressed sparse row format. And in that case, I am allowed to access entries, AIJ. Okay. Now, I want to pull up a documentation for SciPy, or a sparse package. Okay. I'll make this bigger in a moment. Well, I'll make it bigger now. Whoops, bigger, not smaller. Okay. All right. So sparse matrices right here. And here it has a list of all of the functions that are available. Now, it's like creating identity matrix or or you could also create a matrix from diagonals. Notice there's 2 functions here, diags and SP diags. So it's largely for backward compatibility. You really only need one of these, and diags is the one that's preferred. And that's one that I'll use. But so that's one thing to keep in mind. There's different versions of the same thing. Rand and random both create random matrices, but random allows you to pull random data from a different source, whereas rand just does uniform distribution, just like MATLAB's rand. So if I go ahead and look at rand, but I was just using, so you get to specify a format, but as far as like a list of all the formats, that's up here. You can create, this allocates matrices in one of the 8 different formats for sparse matrices that Python provides. So the one I'm just using here, CSR compressed sparse row, similar to compressed sparse column. Chances are one of these is the one that you'd want to use, but there are, again, it really depends on the application. And if you go to the documentation for one of these, like I'll pick out CSR here, there's some commentary about the advantages and disadvantages of that particular format. Now, not all of the documentation pages have these, but at least it's something to go on. So, for example, matrix arithmetic in CSR format, multiplying or adding matrices, that's efficient. Taking slices, accessing rows is efficient. Whereas if you want to access columns, you might want to consider CSC, compressed sparse column, which is similar. Matrix vector products, extremely important operation. You want that to be fast. Whereas accessing columns in CSR, not a good idea. That's why you should use CSC, as I was just mentioning. Also, changes to the sparsity structure are expensive. What that means is, suppose you want to add a new entry. So you have an entry matrix that's currently 0, and you want to put a non-zero entry in that spot. You're changing the whole structure. That is not good in CSR format. So there's LIL or DOK. LIL involves linked lists. And the thing is, you can always change between formats for different tasks. So you have to decide, is it worth it? Like, should you put up with a slower operation in the format that you have, or should you go ahead, change format, perform the operation, and then go back? It's a pain, admittedly, but it pays off in more efficient code if you take the time to do that legwork. Okay. Now, and actually Python can be pretty helpful about these different formats, as I'll show in just a little bit. Okay. Now, I guess what I'm going to do, two operations side by side in the same matrix, solving a system of equations. One as a sparse matrix and the other as a full matrix. So now that I have this 4x4 sparse matrix, I'm going to create AF, which is just the full version of A. Okay. Just so we have it handy. And before I go any further, I want to make sure that it's about to solve systems. I got to make sure it's not singular. So for a full matrix, I can use a SciPy linear algebra package that I imported earlier, and use a determinant. Okay, and the determinant is non-zero, so we're good to go. I can solve systems. Now, cannot do this for sparse matrices. So to give you an idea of what's available and what's not, if we go over to here. Okay, so SciPy linalg is here. Okay, so you can compute matrix inverses, you can solve system equations. Solve is a generic AX equals B, but notice, whereas MATLAB just has backslash and it figures out what to do, here are separate functions for, like, if you know if a matrix is banded or if you know if a matrix is triangular. Then you should do this. Solve by itself, you give it a triangular matrix, it's not going to know it's triangular. It'll go for trouble with Gaussian elimination and all that. You don't want that. So call solve triangular for that situation. Here's a determinant function, matrix vector norms, which is also available in NumPy, but and then pseudo inverse. Okay. Eigenvalue problems, various routines for that, for different kinds of matrices. All the different factorizations, LU, singular value decomposition, Cholesky for symmetric positive definite. All that is here. So QR factorization, updating a QR factorization similar to MATLAB's functions, Schur decomposition for eigenvalues. So ton of stuff. Matrix exponential, all the matrix functions you have. So there's a wealth of routines here. And then different special matrices like a Hilbert matrix or a circulant matrix. And MATLAB has these things too, but but now, but all of that's for dense or full matrices. If I go over to sparse linear algebra, you can do inverse, and then which well, almost certainly destroy sparsity. Matrix exponential, sparse solve, whether it's a triangular matrix or not. You can have the iterative methods, which is something I'll talk about next week, like conjugate gradient or GMRes. And then, or for least squares problems, you can compute select eigenvalues, which you can also do in MATLAB. So MATLAB, you can do SVD for a full matrix or Eig, but you can't do that for a sparse matrix. You have to settle for selected eigenvalues or singular values. So we have that here. But notice, if you scroll through one versus the other, for sparse matrices, there's not a whole lot available. Even like some rudimentary tasks like determinant. Well, actually, determinant's not that rudimentary. It's kind of a pain. It's actually pretty expensive, but actually, they don't even. I think there's not even a norm here. Oh, okay, there is. That's good because that would be kind of crazy if not. Okay, and there's different norms. Okay, so here are the norms that it computes, but notice some are not implemented. So we have a Frobenius norm, we have the infinity norm, which is a row sum, one norm, which is a column sum, and then the 2 norm, matrix 2 norm, is not implemented for sparse. And the reason why is it's the largest singular. Well, it could be implemented because it's the largest singular value, but it can only compute it approximately. So, whereas in MATLAB, I think in MATLAB, I'm going to try this just for fun. I'm going to create a matrix here, make it sparse. Can't do it here either. Okay, so at least the functionality in with norms for sparse or dense matrices is similar in MATLAB versus Python. Okay, so at least you're not getting a raw deal in either place. Now, what's interesting though is if I compute the norm of a full matrix, okay, as opposed to SVDS of a sparse version of A. Okay, the largest singular value is the 2 norm. They almost agree. So if you really want a 2 norm of a sparse matrix, you can get it. It's just not as accurate as other norms would be, because you're using an iterative method. Okay, I didn't really mean to go down that rabbit hole, but the point is, the functionality available in sparse versus full very different in SciPy. But SciPy for sparse matrices solving X equals B, you want to use iterative methods, and just like MATLAB, there are several of those available. Okay, so now that we know a matrix is non-singular, I'm going to create a random vector. Well, I'll just make up a vector B for solving Ax equals B. Okay, so for full matrices, I can do X. I'll call it X full, and I'm going to use a SciPy linear algebra package, and just solve an AB. Okay. Whoa, sorry, I goofed. That's AF. Need to pass the full matrix. Oh, I'm sorry, I goofed. In my notes, I had everything 3 by 3. I forgot that in here today, I've made the matrix 4 by 4. Okay, so let's make B a 4 vector. All right, let's do this again. Solving X equals B, full matrix. Stop that. Full matrices. Okay. Dang thing. AF, full matrix. Okay, third time's a charm. Okay, so that's the solution. And now for sparse matrices, plain old A is a sparse matrix. So that'd be sparse linear algebra dot sp solve, so different function name. And thankfully they agree. They ought to, because likely not necessarily using a same algorithm. That depends, but because Gaussian elimination with pivoting can be problematic for sparse matrices because you might get the troublesome phenomenon of fill-in, where it creates new non-zero entries that weren't there before. Okay. Now, okay, so any questions about creating sparse matrices and solving systems? All right, so this is your backslash. So that's Python, especially for numerical linear algebra, involves a bit more typing.
Yeah. But I presume that you were mentioning that it doesn't go through the same algorithm that MATLAB does with backslash. It behooves one to know what type of matrix one is working with,
right,
and what kind of operation. And if you don't know that,
yeah,
you're going to be really screwed.
Yeah, especially if there's an alternative that's much more efficient for your matrix.
So whereas with MATLAB, it's really nice. In other words, it's saying on the coding aspect, if we're getting a whole bunch of different matrices, we need to start filtering them out.
Yeah, and so the backslash tries to figure out what kind of problem is it really handed.
Oh, yeah, it has a really interesting algorithm.
Yeah, definitely. Okay.
It saves time.
Yep. Okay. Now, let's see. What else do I have here? Okay. All right. I'm going to take a little time here to talk about sparse matrix representation. And I need to pull up in particular the one for coordinate format. Okay. Okay. Now, all right, so I'm going to create another matrix, random one that's in coordinate format. I'll call it B, and I want to overwrite A. Now, COO is a default. I'm just typing here anyway, just for clarity. Now, so in coordinate format, you have vectors of row indices, column indices, and values. So actually, I'll do this in MATLAB also. Might be a little easier to see. I think function. Yeah, SP rand. Okay, so I'll create the same kind of matrix. B equals SP rand. Okay, 4 by 4, same density, 0.6. Okay, now this is coordinate format, which is what MATLAB uses. So if I do, okay, so, and it's organized by column. So row 3, column 1 is this 0.415. Row 2, column 2 is 0.0193, etc. So Bij is equal to this. So we have row indices, column indices, values. Now, if we take a look at this B here in my Python console, well, to print it out, I need to do this. Although, actually, I'm curious, what if I do print B? I haven't tried that before. Oh, this is convenient. It shows it as MATLAB-like format. I just have to take into account, well, I want to have it, okay. So So what we have here is row 2, column 1 is equal to this. And then, but notice it's not organized in exactly the same. Like the ordering is different. It seems to jump around. Like the first entry is this one. The second entry is this one. The third entry is this. It jumps around. Whereas with MATLAB, it's organized by column. Now, really, that's an artifact of how RAND works, of a random generation of sparse matrix in both MATLAB and Python. You can have these ordered in any way you want, and to represent the same matrix. Okay. Now, what's nice about Python, though, is unlike MATLAB, you can access these individual pieces of its representation as attributes. We've seen some attributes already, like NNZ and shape. So if I do b.row, so what we have is, this is a list of all the row, or actually numpy nd array of all the indices. 1 3 0, 3 1 2, 3 2 0. So all of that is here. There's also b.col that has all the column indices. And then b.data that has the actual entries in here. So all of these are exposed as attributes of the sparse matrix. So what you could do is you could try, well, assuming you can try this, I'm going to try it now, just for fun. I'm going to see if it lets me modify one of these things. Okay. Like if I want to change an entry, I'll change this entry to pi. Let's see if it lets me do that. It might not. It did. Oh, this is precious. Okay. Yeah, so now that entry is equal to pi. Now, I'm going to try something more nefarious. I'm going to see if it'll let me change b.row. Like here, the first entry is row 2, column 1, and that's where the pi is. I want to put it in entry 1, 1. So I want to change this 1 here to a 0. Let's see if it'll let me do that. b.row 0 is equal to 0. Okay. Yep, it did. So now if I print out the matrix again, and it has moved the entry. So that's another way to mess with sparse matrices in the coordinate format. Okay. Oh, that's weird. The entire fourth column is 0. So this matrix is very singular. Okay. Now, by contrast, Csr format. So A is in Csr format. Let's see what happens if I print out A. So printing actually converts to COO for display purposes. So this doesn't give you any information about what the CSR representation is like, compressed sparse row. So for that, we need to look at its attributes. So for these types, like COO matrix is the name of a type, you can see what functions are available, like how you make one, an object of this type, examples, and attributes. Like this is what I was doing for coordinate format, .data, .row, .column. So now I want to do the same thing for CSR. Okay, so here's how different ways of creating a CSR matrix from given entries. Usage. Okay, here are the attributes that are different from COO. So I want to look at these. In pointer, indices, and data. So if I look at the matrix's way it normally looks, and now I look at A in pointer. Okay, so what exactly does this mean? It gives you an idea of how many non-zero entries there are per row. So the first element of this will always be 0 because you're always going to start with a first row. The second element will be the index of a first non-zero entry in the second row, third row, fourth row, and then this will always be equal to the total number of non-zero entries in the matrix. Now, it's easier to understand if I show you the next item here, the next attribute, indices. Okay, this indicates the column indices of all the non-zero entries in order by row. So entries 0 through 2 are the first row. They're non-zero entries in columns 1, 2, and 4, and that's what we see here. At location 3, as indicated by in pointer, so starting here, are the column indices for non-zero entries in the second row. So columns 1 and 3, so we see that here. And then index 5, which is the sixth entry, indicates column column indices of non-zero entries in row 3, and then in row 4. So the idea is so non-zero entries in row I are found in elements indices in pointer. Actually, I'm going to repeat this comment. I need to be clear about my indexing convention. So by row I mean in conventional mathematical sense, row 1 to m. So mathematically, I'm doing one-based indexing. Are found in okay, so indices ranging from in pointer element I minus 1 all the way to in pointer I. Keeping in mind that this is a range in Python, meaning that this value is not included. It starts from here all the way up to this minus 1. So for example, indices in pointer 0 up to in pointer 1. Oh, sorry, I need to do a dot everywhere. Okay, and what that does is it extracts those indices for the non-zero entries in the first row. And this is why this entry has to be here, because that way this expression will make sense for all rows, including the last row. You can always just use this to get those entries. So now if I print out the matrix again and look at a.data, it has all the entries organized by row. So first row, second row, third row, fourth row. So by understanding CSR format, you automatically understand CSC format because it works exactly the same way, except like in a transpose, that it's organizing everything by columns. So we have, so indices has a list of, in that case, row indices rather than column indices. It's a bit of a pain to wrap your head around, but from looking at enough examples, you get an idea. So for example, all non-zero entries in the second row, I could do a.data and do a.index pointer 1, indicating the second row because it's zero-based indexing, a in pointer 2. And that'll extract the 2 non-zero entries in the second row. But that tells me nothing about where within the second row they are. That's okay. I can access a.indices, and that tells me that they're in column 1 and column 3, like we see here. Okay. Nothing to it. Okay. All right. Let's take our first break. Okay. All right. So now, let's for an example of a, or actually a couple examples here. Suppose you have a matrix that you know is banded. So all the non-zero entries are confined to certain diagonals. So we can use the sparse function diags to do that. So I'm going to create. So we use scipy dot sparse dot diags for this purpose, similar to MATLAB SP diags in terms of the usage. Now, if I go over to MATLAB and I want to create a okay. Okay. I forgot my MATLAB common character. I'm going to create the matrix. I think I'll make this a little bigger. Or can I? Oh, yeah. All right. So I'm going to type a matrix in as a full matrix, and then to create a sparse one. All right. So the suffix f will be for full. And I want different entries along the diagonals. So something like, I'll just make something up. I'll make it a 5 by 5. Okay. And try diagonal. 0, 0, 12, 13. Okay. So that's matrix as a full matrix. So if I make this matrix, so the main diagonal will be everything here 1, 4, 7, 10, 13. Okay. The sub-diagonal down below 3, 6, 9, 12. And then the super diagonal, everything above 2, 5, 8, 11. Okay. Now, one of the things I found a little bit annoying about MATLAB's SP diags is it wants you to specify the diagonals as columns. So like subdiagonal. Oh, actually, these are row vectors. I need them to be column vectors, so I'll transpose them. Subdiagonal, main diagonal, super diagonal. And then I put them on diagonals -1, 0, 1, make it a 5 by 5 matrix. Now this, as written, is not going to work. Can anyone tell me why? It's going to give me an error. Or you can try it yourself and maybe it'll tell you. Well, the error message might not be so clear.
Yeah, you're creating an array of columns, and they're not all the same size.
Yeah, the main diagonal is 5 entries.
And the
It
other
has
are
4. So what do you? So yeah, these tiles have to be the same length. So I need to pad them somehow. Now I'll make this a little bigger. Like for instance, I could just pad by zeros. But what I don't know is, do I add the 0 on the beginning or on the end? Okay. So if I do this, oh, appears to be correct. Wait, I'm going to put up the command again. But full. Okay, and this is correct. So for SP diags, pad end of subdiagonals with zeros and beginning of superdiagonals with zeros. Then you get the correct result. Okay, so now I want to do the same thing in Python. So the function that we're going to use is diags. Now, in previous classes, you don't have had students work with SP diags is to create like it's called a tuplets matrix, where every entry along a given diagonal is the same. So you just could create a vector of 1s and you're done with it. So you didn't have to think about this before. Okay, so if I look at diags, here we are. Okay. So here you're passing a sequence of arrays containing the matrix diagonals. So in other words, what it suggests is it's a bit more sensible, but you don't have to do this padding with zeros. So what I'm going to do is I'm going to create the well, notice this sequence of array-like. It doesn't have to be an actual NumPy ND array. So for instance, something like a list that could be converted to an array. So not having tried this before, let's see what happens. Okay, so I wanted to create the same diagonals as I did in MATLAB. So main diagonal would be, I'll just make it an actual list. Okay, I need to put MATLAB back up. Okay, 1, 4, 7, 10, 13. In fact, I can use the same syntax, except I need the commas. And then the subdiagonal is 3, 6, 9, 9, 12. And a super diagonal would be 2, 5, 8, 11. Okay, so I'm going to create a banded matrix. I'll call it the SP diags. And I'll have subdiagonal main diagonal, super diagonal, placed on diagonals -1, 0, 1. So just like in MATLAB or Python, or just like in MATLAB, Python identifies diagonals as the same. 0 is the main diagonal. Positive numbers are super diagonals, and negative numbers correspond to subdiagonals. And the shape I want is a tuple, so 5 by 5. The shape argument is optional if, and I didn't really need it in the MATLAB command either, but so if you don't include shape, it'll figure it out. Like basically the smallest matrix that would contain whatever you specify. But I find it's a good idea to just have it just so it's clear what's being done. So if I go ahead and do this, please work. Okay. And, oh, I have to do this to print it out. And here it is. So I didn't have to do any of this padding stuff. So that was nice. So Python's more flexible than that because you can create lists of elements where the elements themselves can be of different types, arrays of different lengths. Now, MATLAB kind of has the same thing with cell arrays. But actually, one thing I'm curious about is if I try the same thing in MATLAB, where instead of trying to make these into a matrix, which it won't let me do, I wonder if it'll let me do this. I haven't tried this before. Put them in a cell array. The curly braces indicate cell array. So then the elements of a cell array can be of different types. Let's see if it does that. Oh, didn't like that. Interesting. Okay, never mind then. So, bottom line, it's easier to do in Python. Okay. All right. So that's how you use diag. So you can have a list of diagonals. The diagonals themselves can be NumPy ND arrays, or they can be lists. It doesn't matter. It'll work either way. Your indices and then indication of the size of a matrix, unless you've given enough information for it to figure it out. Okay. Now, there's one other thing about sparse matrix creation in Python that's particularly nice. So I'm going to try to do this in MATLAB first, and I imagine it won't let me. Create a second derivative matrix up to a scaling factor. So -2 on the diagonal, 1 on sub and super diagonal. Now, I'm going to try this, where SP diags. I'm going to make it a 5 by 5 like before. I'd like to do this. Put 1, -2, 1 on diagonals -1, 0, 1. And make it a 5 by 5. But let's see what it gives me. Yeah, didn't like that. The reason why is I just put numbers here for each diagonal. I needed to put vectors in here. So column vector, like a column vector for a subdiagonal, column vector for a diagonal, column vector for a super diagonal. However, it turns out something like this will work in Python. Okay. 1 -2, 1, +1, 0, 1. Shape. Oh, actually, I'm going to. Oh, hold on. I want to make a size of variable. What I'm about to do here is going to set the stage for what you'll do in either later assignments or maybe the default project if you can't think of one of your own. Like something involving solving PDEs. So I'm going to solve a 2-point boundary value problem using finite differences. So I'll make a 5 by 5 matrix, so n by n. Okay, so 1's on the subdiagonal, -2 on the diagonal, 1 on the super diagonal, -1, 0, 1. So sub, main, and super. Shape equals an n by n matrix. Okay. Now, there's no error anyway. And notice it's a different format. It's not coordinate format. It's not compressed sparse row. It's diagonal format because of diags. So by default, it will create a sparse matrix represented in this format. Now, let's print it out. And sure enough, it's correct. So, diags was smart enough, Python's diags was smart enough to take these numbers that represent the diagonals, 1, minus 2, 1, and understand that what I really wanted to do was have all 1s on the subdiagonal, all minus 2s on the main diagonal, all 1s on the superdiagonal. So this is an example of broadcasting. And that's discussed in here. Okay. I know I saw it earlier. Yes. Broadcasting of scalars is supported. So in fact, what I did in my console is exactly the same thing here, just a different size. So broadcasting of scalars means taking a scalar and expanding it to be a vector or matrix for some operation. For example, suppose you have a n by n matrix and you do like +1, and you really want to add 1 to all the entries. So Python broadcasts that 1 to every entry of a matrix to add to the other one. MATLAB does broadcasting in certain situations, like matrix addition, or, for example, but not this one. So that's one advantage of Python that's more convenient for creating these kind of. This example of a Toeplitz matrix where all the entries on a given diagonal are the same. But notice you have to specify the shape, which makes sense because if you're telling it, I want to put these numbers on these diagonals, it doesn't know how many you want unless you tell it using the shape argument. Okay. All right. So it broadcasts those scalars across the specified diagonals. Okay. Now, here's a problem though. Suppose I want to access an individual array entry, like a 1-1 entry. Can't do it. So just like coordinate format, the diagonal format, not subscriptable. So because I'm going to want to mess with its entries later, I'm going to recreate it and specify a format. Format equals CSR, just so I can access entries. All right. So now what I'm going to do is, for this next example, I'm going to solve a 2-point boundary value problem. U double prime is equal to, it's a very simple one you can solve by hand, in fact, sine 2x, and u of 0, okay, so on the interval 0 to 1, no, actually 0 to 2 pi. Actually, I'm just going to make this pi. That'll work too. Okay, and then the boundary conditions, u of 0 and u of pi are equal to 0. So the exact solution is 1/4 or minus 1/4 sine 2x, because differentiate sine twice, it negates, but then by chain rule, you're multiplying by 2 twice, so that 4 cancels out this 1/4, and you end up with sine 2x. So I'm going to use that knowledge to check. So I want to solve this using finite differences. And actually, I'd like to have more grid points than just 5. I'll make 10. And then I'll recreate this matrix that's now 10 by 10. So we're going to use a grid with n interior points in the interval 0 to pi, equally spaced. So the spacing is going to be dx will be the length of the interval, which is pi, or math pi, divided by n plus 1. So in other words, you have n interior points, so that'd be n plus 1 subintervals, and you also have 2 boundary points. But so now I'm going to make a vector of x's, interior x values. So that would be so x equals dx times the integers from 1 to n. So that would be I'm going to use NumPy a range starting from 1, and I want to go up to n, so I put n plus 1 as the ending value, because it'll always stop 1 short. Okay, so now I'll make the right-hand side. Now, you might think I want sine 2x, so you might think, oh, okay, I'll just put math.sine of x, but that's not going to work, as we talked about last time. This function, math.sine, is not vectorized. So what I have to do instead is I'm going to vectorize it. So now, what I'm highlighting here, the result of numpy.vectorize, is a new function handle that is now applied to x. So that will work. Okay. But the thing is, the standard difference matrix for second derivative with Dirichlet boundary conditions. In other words, boundary conditions specified at the specifying a value of a solution at the boundary points is not the matrix D that I created, but rather dx squared, or sorry, 1 over dx squared times D, because center difference is that u double prime of xj is equal to 1 over d delta x squared times u of x j minus 1 minus 2u xj plus u xj plus 1. So the coefficients of these u values, 1, minus 2, 1, that explains the elements of D. This Topless matrix has minus 2s on the diagonal, where the indices are the same, 1s on the super subdiagonal, where the indices differ from j by 1. But I forgot the 1 over delta x squared. So here's, that's okay. What I can do is I will solve du is equal to dx squared times f. In other words, I'm just going to take that 1 over delta x squared and move it to the other side. Problem solved. So I'm just going to multiply that dx squared times f. Okay. So now I'm able to solve my system. So my solution is equal to, so psi pi sparse lin_alg that I've imported earlier dot sp solve d and f. And based on my notes, this should work. Okay. Now, is this correct? Let's see what we have first. It's a NumPy ND array, as expected. Now, I also want the exact. The exact solution would be equal to -1/4 times, I need to do a vectorize. Oh, I'm sorry, I goofed. I have a wrong right-hand side. I needed to do 2x, not x. Okay, hold on. Okay. And then I need to do that. Okay. All right. So now my exact solution is going to be -1/4 times numpy.vectorize sine applied to 2 times x. Okay. So if we look at exact, that something's wrong. Okay. What happened? What's sad is I had this all worked out for a slightly different example that actually involves sine x. And I just thought, oh, I'll change the number to make it more interesting, and this is what happens. Okay, because the x values go from 0 to pi, interior points. Sine 2x on 0 to pi should be positive and negative. Okay. My dx is pi over n plus 1. Okay, so that's the interval 0 to pi. Okay. If I what? Oh, sorry, dot plot. Okay. Okay, that's extra weird. Oh, I'm such an idiot. That's the wrong u. When I had sine x, I go ahead and solve it, print out u. Then I realize, oh, I have a wrong right-hand side. Made the correct right-hand side. Solved the system again. Didn't bother printing out that solution. No. Okay. Wow. Okay. Here's the solution that's computed. Yeah, and you see they agree quite nicely. It's driving me batshit. Okay. All right. Okay. Well, that's okay. I don't see anything wrong here because there wasn't, except for what I was looking at for printing it out. Okay. All right. So now I'm gonna have a mess in my history log here. Okay. So, all right. So I do all that. Okay, that needs to change to 2x. And then get rid of. I wonder if it lets me. Get rid of stuff. I don't. Oh no, it doesn't let me modify this. But when I post it, I will clean it up. So my erroneous gobbledygook is not in here. Okay. All right, so sorry, I cannot type today either. Okay. All right, so that's a spacing in an interval AB, which in this case is 0 to pi. Okay, I just want to have a clean record here and a little clearer presentation because, okay. And the general formula is A plus dx times 1 to n. Now this is for Dirichlet boundary conditions. Cannot emphasize that enough. If you're doing something else like Neumann or periodic, that would be different. Okay, because you'd be including one or both boundary points. Now in our case, A is 0. Okay. Okay, so we have our differentiation matrix for second derivative. All right, so that's the approximation in this case. So D is, now, it doesn't really matter whether you have the 1 over dx squared on the left side or dx squared on the right side. Here I'm doing it on the left side just to agree with this. It's all equivalent anyway. The Csr format is not absolutely necessary for what I'm doing here because all I'm trying to do is solve Ax equals B. You can use any of the formats for solving Ax equals B. Now, which one is most efficient is another matter. Okay. And then inside as function of x. So, all right. So in this case, I want sine 2x. And then solve system. Okay. Okay. So for toy problems like this, basically just to test your method. And then we can go ahead and okay. I wonder if, okay, I'll try this in a moment, but and just to make dang sure that everything is correct. Okay. Now, if I had done this like over here in a script, like these two plot statements followed by a show, it would put those on the same plot, which is actually what you want for the assignment. So its default is to hold on rather than hold off. Okay. But what I'm wondering is, okay, and this is something I have not tried before. Oh, so that's convenient. I plot exact versus x and u versus x, and we'll put both on the same plot. So you can do that for, if you want to do a list of things all in one command. And you can see they agree pretty well. Now, I don't think an error estimate, np.lineage.norm of oh. Okay, using numpy.inf to specify infinity norm. And there's the norm of the error, so 0.007 roughly. Now, I'm going to do this again, except now I'm going to set n equal to 20. It was 10 before. So now if I step through this again, okay, so I need a new dx, a new x, a new d, a new f, new computed solution, a new exact, Okay. So what will happen here if I compute the norm of the error? Okay, so I'm going to take this value divided by this value. So the old error divided by the new. 3.66. So the error decreased not quite by a factor of 4, but pretty close. The standard difference or second derivative is second order accurate. So as you double the number of grid points, although actually, now that I think about it, the spacing is not cut in half because I'm dividing by n plus 1. So the spacing is almost cut in half. So just for fun, I'm going to try this with, instead of 10 and 20 grid points, I'm going to try with 9 and 19. Okay, so 9 dx x d f u exact norm. Okay, roughly 0.008. Now if I make n 19, now the dx is going to be exactly half, because the first dx is pi over 10. The next dx will be pi over 20. Okay, so I set to 19 dx x d, thank God for history scrolling, f u exact. Oh, and then the norm, the error. Okay, yeah, so now that factor looks to be much closer to 4. Okay, yeah, getting there. And it would get closer and closer to 4 if I let the number of grid points increase even further. Okay, so here I showed you how to solve a simple 2-point boundary value problem using finite differences. Now, combining this with time-stepping methods, like for your first assignment, to working with a matrix based on this, for example, like identity plus delta t times this D matrix for Euler's method, you can now solve systems of ODEs that come from PDEs. So that's what I have in mind, like for a default project, as trying out various PDE methods based on combining ideas from solving initial value problems and for the time part, and then boundary value problems for the spatial part. Okay, let's take our second break. Okay, well, we don't have much time left. Oh well, bummer. But I'd gotten through all the examples I intended to anyway. But now, if you keep in mind that only half the students in the class are actually here in the room, you have, well, 4 students who are always taking it remotely, and 1 who happens to be doing this week. So that's why if you have questions about the first assignment, it's possible that those questions may be of general interest to the rest of the class. So that's why I would encourage you to voice such questions so that they can be included in the video. Does anybody have any?
I don't have a question, but I have one thing that I discovered.
Yeah.
Using the array format, even though for scalars, say having a variable, say y plus equals some quantity, it works better for arrays. You have y equals y plus.
Oh, does it give an error or something, or?
It doesn't compute properly. Sometimes it would bring up an error. Sometimes
maybe that's why I had it written that way.
It might have been.
I don't remember. Yeah.
All I know is that something about my very much haphazard code had problems with it, and when I changed it, I stopped having problems.
Interesting. Well, let's try an example right here. If I make a couple 5x5 or not 5x5, 5-element vectors. Okay, so now I want to save the originals. Oh, I have to be careful. X dot copy. Okay, so if I do x equals x plus y. Okay, and then I restore the original x and y. And then I do x plus equals y. Okay, so no difference in that case, but it wouldn't surprise me. I feel like I had some reason for doing it that way. And it may have something to do with the fact that when it comes to assignment of dealing with arrays, that's passing addresses and so forth. So even though this individual operation that I've shown you right here is fine, when you're using variables for various things, it could, Unfortunately, I wish I could remember. What I will do when I have a chance is go back to my solution and put it using the plus equals and see if some problem occurs, and that might highlight why. Because I remember one case I had some unusual behavior that it was often just 1 point or something. It was kind of strange. Like dealing with the initial condition was wrong. Okay, that's something that's worth looking into. But, okay. Any questions about the assignment? Everyone's just proceeding swimmingly, or has not yet really started.
I know it was just so easy. I just looked at it. It's like, oh my gosh, this is just.
This just writes
so
itself.
Obvious. Just kidding.
Okay. Funny. Okay. Well, there's certainly having forward Euler there. 4 forward running cutoff should be pretty quick. The others would take somewhat more time. Okay, and as far as submission goes, I said it was due Tuesday. It doesn't have to be by class time on Tuesday. So if you have difficulties, then you can bring them up then during class. So, but yeah, you're all the undergrads, so shy to ask questions in class. Dang it. So, all right. So that's it. Or you guys just want to be done? I know I want to be, but yeah.
And as far as this onward too, that's going to be posted next Tuesday.
Yeah. So I still have to actually compose the assignments, and yeah.
So no sneak previews.
Some of the comments I made today give an idea, but yeah. So what I'll be doing on Tuesday, describing the assignment. Well, just as like last Tuesday, I described the assignment and also took some time to cover adaptive time-stepping methods. So on Tuesday, I will take some time to go over iterative methods and something new, because those of you who were in 561 and saw like stationary iterative methods like Jacobi, Gauss-Seidel, but I'll take some time to talk about conjugate gradient, which I think I covered in 610. Yeah, I did, because it took a long time. So, yeah, it'll be a somewhat abbreviated presentation, but there's a wealth of information in my book.
Oh, yeah.
So, yeah. So, okay. Well, I'll be sticking around anyway, just because I have to upload the video and all that. But yeah.
I do have one more question.
Yeah.
And this is about the assignment.
Yeah.
For the final project, I'm a little bit vague as to what you're really looking, the level of complexity for what you're looking for.
Yeah. It's hard to give like abstract criteria for that. Basically, I just wanted to be challenging, but and I guess it's something where mainly I'm interested in what subject matter are each of you going to choose? And you might have some idea of what the task would be, and then once you describe it to me, and I get an idea of like, oh, how involved this might be, then we might adjust the scope one way or another. So, um, so more ambitious is usually better, but to a point, just because of time. So, yeah, so it's something that we'll hash out. Yeah. So yeah.
So the operative word is keep in touch.
Yes. Yes. Yeah. Alrighty. Okay. Away we go. Okay, I'm adding this post-class supplement. It's really a continuation of a discussion that happened at the end of class about the distinction between x equals x plus y and x plus equals y, which is operations you'd think would be equivalent, but it turns out when you're dealing with NumPy ND arrays, they are not. Whereas with scalar variables, yes, they are equivalent. And so what I did was I ran my solution on the system of ODEs and found that using plus equals did not produce a correct solution, whereas using just y equals y plus something, so writing it out like that, did produce the correct solution. So I want to give you an indication as to why the behavior would be different by stepping through a simple example. So I'll import NumPy here. I'm going to create a random vector x, random vector y, and then I'm also going to create vector z, but I'm just going to assign z to x. Really, I'm assigning x to z. So, so if I go ahead and print all of these out, so x, y, z, with x and z, of course, being the same. And then what I'm going to do is I'm going to do z equals z plus y. So now after I carry that out, of course x is the same, y is the same, and z has now changed because these two have been added together. So, so z, which was a copy of x, now has y added to it, and we get this. So everything here works as you would expect. So what I'm going to do now is I'm going to do this as if it's a fresh example, recreate all of these. Oh, sorry. And then assign x to z again. And now I will do z plus equals y. So before we had z equals z plus y, here is z plus equals y. So you think, okay, how should this be any different? But if I display x now, x has changed, even though this operation had nothing to do with x. And here, it still matches z. So, changing the content of z using this operation also happened to change x. And the reason for this has to do with in Python, assignment happening by address. So here I'm saying z equals x, and what that does is that has the effect of copying the address of x to z. So now we're pointing to the same location in memory, and which therefore pointing to the same numbers. So then when I modify z, because the address of z and the address of x are the same, that has the effect of modifying x. So what about the example up above? If we go back to that, how come that did not happen in this case? The reason why is the values of z and y are added together and stored in a new temporary variable, which at the time of the addition does not have a variable associated with it. The address of that temporary location where the sums are held is now assigned to z. So whereas when this happened, z and x had the same address, now they don't anymore. So z is, after this operation, z is now pointing to a new address that contains the sum of these numbers. X is still pointing to the same place as it was before. So the bottom line here for the assignment, use y equals y plus, not y plus equals. It's fine for scalars, but not for NumPy ND arrays. So as an example, for Euler, which I have earlier, y equals y plus h times f of ty. And I know I originally had that, and I believe it still says that on the site, but I'm going to make sure of that. So that, well, actually, if I go ahead and open that up now. Okay, so the ODE solve that was actually posted. Okay. Okay, yeah, so it should not say this. This will not work for systems. So y plus. T plus equals h is fine because they're scalars. So I'm going to update the site with this. So be sure to take this into account as you complete the assignment. Otherwise, it won't work for the second example of a system of 2 ODEs. Okay, so now I can really end the video and get all this posted for you.